phys2212lab3. Introduction. So the purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel, then use multimeters to measure the actual values of conventional current and potential differences in the circuit, and then examine the behavior of ohmic resistors and capacitors. Some models and fundamental principles would be the energy conservation or loop rule, current conservation or charge conservation, and the definition of steady state, and Ohm's law. Some quick results. We got a current of 20 milliamps. 47 ohm resistor potential difference was 0.9 volts. 100 ohm resistor potential difference was 1.95 volts. And it took the 10 ohm bulb 12.3 seconds to charge and 12.6 seconds to discharge. And it took the 20 ohm bulb 23.85 seconds to charge and 30.2 seconds to discharge. Main physics ideas and models. So first, conservation of energy. So loop rule. The potential difference around the circuit must add up to 0. So you just sum up all the elements and their potential differences. Also, conservation of charge or node rule. So the sum of the currents going into the node must be equal to the sum of the currents going out of the node. Also, at steady state, there should be no accumulation of charges inside the wire. Also, Ohm's law, V equals I times R. So the current through a conductor at 2 points will be directly proportional to the voltage between those 2 points. So the system for the first experiment is the 2 batteries, the 2 resistors, the 2 ammeters, and the wire. And for the surroundings would be the universe around the circuit. And the initial conditions for that would be the initial voltage is 0. So for assumptions, just assume that the wires are undamaged and have no internal resistance, and also assume the multimeters are accurate. For the experiment 1, you can see this up here. Based off the math using V equals IR, we thought that the current would be equal to 0.02 amps, which is what we got. And then also here we were able to determine the resistance of each circuit element using the V equals IR formula. And we got, for the 47, we got 47 ohms. For the resistor, we got 100 ohms. And for the wire, we got 0 ohms. And for the ammeter, we got 0 ohms. And then if we look at the voltage from between every 2 points and we sum them together, we can find the actual potential difference and also the expected potential difference. So the expected potential difference would be 0, but according to our measured potential differences, our actual total difference was 0.03, which was still fairly close to 0. So for experiment 2, so we had a circuit with 2 1.5 volt batteries, a 1 Faraday capacitor, and a 10 and 20 ohm light bulb. The system was 2 batteries, the capacitor, the light bulbs, and the wire. The surroundings would be the universe around the circuit. So we connect each light bulb to a battery circuit, and then we measure charging and discharging period for each light bulb. So for the 10 ohm bulb, it took 12.3 seconds to charge and 12.6 seconds to discharge. For the 20 ohm bulb, it took 24 seconds to charge and 25.2 seconds to discharge the capacitor. So yeah, it's time-dependent voltage across the discharging capacitor, and we use this location that was provided to us in the lab document. And here we were able to predict the RC circuit. So we got 6 as opposed to our predicted was 6, but we really got 6.37, which was still fairly close. Discussion. So yeah, the experimental and predicted results were fairly similar to each other. Some possible sources of error would be the human reaction time of the stopwatch during the charging and discharging of the capacitor, and also this would mean that that the voltage would be slightly inaccurate since it's time dependent. Also, the online simulations and calculations do not perfectly mirror real world scenarios. So perfect conditions of the model that we use to calculate this does not account for conditions like damaged wires. But what if you charge the capacitor with no resistor in the circuit? How quickly would the ideal model predict a capacitor to reach full charge, and would this prediction happen in real life? Without resistors, the model would predict that the capacitor would charge instantly. But in the real life, the wires and battery would have some internal resistance, so it would not charge instantly in real life. So when we tested this, it took about 5 seconds to charge. Thank you.